Good morning, everyone. Hope everybody's still refreshed. I know we got a long day to get through, but yeah. My name is Jordan Johnson. I'll be a senior this year at the University of Alabama in Huntsville. I worked along my advisor Yaje Yuan, and this is what we've been doing for the past 8 weeks. So we're talking about like fast radio bursts from galactic magnetar. First, let's just dive right into it and talk about like what is a fast radio burst. But before that, let's give you a brief overview, like seeing like these are points I'm going to be hitting in this talk for today. But yeah, fast radio bursts. So what are fast radio bursts exactly? So these are these bright emissions that happen in millisecond durations within the radio end of the spectrum. The overall reason behind like where these sources come from is generally unknown. We don't know where these come from. We just know that we have all these data from fast radio bursts coming from out in space. And we detect these through these like two instruments that we use. One being CHIME, it's the Canadian hydrogen intensity mapping experiment they have there. And there's the Parkes telescope out in Australia. That's the observatory over there that we use to detect these fast radio bursts. Yes. Yeah. Yeah. So over time, we've consistently gathered all this data from these extragalactic signals. So far, we haven't detected any sources coming within the Milky Way galaxy. But recently, we have received a fast radio burst within our own galaxy. And one way we've detected this, or at least one reason why we're able to detect this is through these it's like potential sources. And so back in 2007, this was the first known fast radio burst to pop up, but we still didn't know like where they come from. So we radio astronomers have tried to find out a way to figure out where these come from. One potential source would be neutron stars, and the neutron stars, given their essential like the process of their creation with the collapse of this collapse of this like gigantic star, forcing all the particles to collapse in to come together to produce these neutrons, giving it the hence neutron star. The overall magnitude is an energy output, and the time scale that these neutrons like release energy has been consistent with the readings and the data we've gathered from fast radio bursts. So that's part of the reason why we think neutron stars are like one of our potential sources. And this object that we received this fast radio burst within our own galaxy is a neutron star. Specifically, it's a galactic magnetar. And so what a galactic magnetar is just this neutron star with a huge, strong magnetic field. And so the interesting thing about this particular magnetar is that we received an X-ray emission along with two radio emissions. And so with these like this particular event, the energy output is very consistent with like how we think fast radio bursts come about, how we detected them and observed them. But to say, with these like observations, like as we gather more data, we can like provide more evidence about like how this fast radio burst came to be with this magnetar. So let's get to the next slide. And I'm also going to talk about like how we predict that these fast radio bursts have come to be. And so one way we think that these come through a form called an alpha wave. And so this guy back in the 1940s, 1942, Hans Alphen decided like, let's take the mathematics of fluid dynamics and the mathematics of electromagnetism and combine them together to essentially state that plasma has a wave-like behavior. And so one method that we think that came about is that on the surface of this magnetar, there's like something called like a starquake, similar to an earthquake, happens on the surface of the star from like a small region. You shake this little region, and this region produces this energy, and it comes in this form of this alpha wave here. And so, in this like video, a little snapshot here, this energy jiggle from that little jiggle sends energy through this alpha wave, and the alpha wave acts and behaves like a string. So get that one picture in your head, it behaves like a string. And so that being said, the string like oscillates, and you have these little forces that try to bring it back into back to rest, normal state. And so these all behave on these magnetic field lines from this magnetar. And so this is one particular snapshot of this data. As you can see here, you have on your y-axis, you have your Z component, gives you a top-down view of like what is alpha waves being projected from this magnetar, and then R just calculates the radial difference from the magnetar all the way out to this magnetosphere, and you can see the magnetic field lines here, and these three plots are different. They have different bounds here, which correspond to the video that didn't play, it corresponded to like the colors on the alpha wave, the amplitudes, the red end being the positive end, blue end being the negative end. And so as the alpha wave progressed from the magnetar, as I said, that little starquake, it released that energy and alpha wave was projected. And as it moved through the magnetic field lines, these magnetic field lines will be disturbed and be adjusted at a certain point in this process. Those field lines will start to break, quote unquote. And these little points where it breaks shows up these forms, these ejecta, these plasmoids here, little closed loops of these magnetic field lines that hold these pockets of energy. And as it progresses, the alpha wave will basically create this like a little shock wave. And we think through this process, the little shock wave can give us the reason why these fast Fourier bursts occur. Yeah, this is from -10 to 10, -20 to 20, -40 to 40. So what does this all mean? What it all means is that by adjusting the parameters of the amplitude of this amplitude of the alpha wave, we can see the energy output, meaning like how it affects the trajectory of this alpha wave. Because during this whole process, I was able to adjust the amplitude and also adjust the angle range where this alpha wave was being released. So like in that particular like snapshot, those plots, the angle range was from like 0.2 to 0.4. I was able to change that to like 0.4, 0.6, and it basically got it along the equator, and that totally gives you different reading of like how the plots will work out. So the actuality, depending on where you release it, depends on how much energy you need for those plasmoids to take effect and create those like little shock waves. And so in the future, we look to change even more parameters and also incorporate even a 3D part. As you saw, use just in a 2D format, and along with 3D simulations, there's more parameters to dive into. It can get a little complicated. But with these challenges, we will also have more realistic results. You get to see like where can we move on from that point on. And hopefully, with further testing, we can use these predictions to make comparisons with our observational data and look to see like what more simulations and more more ideas of where these fast radio bursts come from. Yeah, thank you. Thanks to everybody who came out today. Thanks to Casey, to Abigail, everyone in CCA, my research advisor, Yajay. It's been a pleasure. So thank you. So, any questions? Yes?
Okay. So where do I start? Okay, so magnetars are the neutron stars that rapidly rotate, right?
Yeah.
Okay. So one question that I have is like, do they have polar jets? Is it possible that this energy is coming from like the poles, and also like when you think of this, so this is like a really high energy event, and we're seeing it as in radio waves, you could say, because it's just really far away. And is this? Would you say like this is like similar to how like the sun has like corona ejecta and all of that, like similar things, but just different places or locations? And I also want to know, do you believe this theory? Do you think that there's like another source for this? Because I mean, this is really, to me, it's a mystery. I feel like we don't really know.
For the first part of your question, I am not too sure. But our simulation is mostly focused on just releasing it from these different angle ranges. As far as like being released from the polar ends, I'm not too sure. So I can get back to you on that. For your second part of your question, it is similar to how like corona mass ejections like take place. Yeah, all this like pertains to like our star, and other things pertain to like the neutron star. So everything is similar still. As far as if I believe in this, the other way to look at it and like try to detect these things, I'm open to new ideas. The great thing about this, the great thing about like science is that you have to be willing to be open to new ideas, to test out new things. So anything constant can always be changed by a new discovery like any day. So like, oh yeah, I still believe in this data that we took in and observed. But I'm also open to any new ways we can like corroborate our data, and make make people understand what fast radio bursts are and where they come from. So, yeah, thank you for the
I
question.
have one more short question. Do you they're becoming like increasingly like more observed, right? Like we are seeing more FRBs than
Yes.
before. So do you think that it's just because we're looking for them, or because the instruments are better, or why do you think we're seeing more than like, 7?
I think it's because our instruments are more up to date. Like I said, with Chime was really relatively like um, recent that it's just been built. But like they take in they do like high mapping like of hydrogen gas. But they take a sweep in from like about 200 to 400 like degrees, and a high frequency band of like 400 800 megahertz. And so like with all that, and looking at a particular sector of the universe, they were able to still like find all these like fast radio bursts. So like yeah, I believe that our instruments will allow us to bring in even more data from fast radio bursts now that we have the technology to do so. Yeah.
Well, yeah, just I mean, I know the history on Chime. Actually, reviewed some of their proposals and things. It's really amazing, right? So they built this primarily to do, as you said, the H1, right? They're doing cosmology. They realized after these FRBs were being found in Australia that they had built an incredible instrument for FRBs if they would wrote the software. And the big challenge was, which is like an enormous amount of data. And like Kendrick Smith, who I know wrote key parts of the software, like went into like assembly language and like understood exactly how to make things run fast. And it was a real software optimization problem. And only by doing that The hard part wasn't the hardware engineering, though the hardware is impressive. It was the software engineering that once they did that, they're discovering these FRBs at an incredible rate. And there's a sister project, Hyrax, that's being built in South Africa. And that's been designed from the beginning to do FRBs. And so I think this is going to be an area where the data is getting better fast, and is just going to continue to accelerate. Yeah, he was working on this here. Yeah, on sabbatical.
Amazing, man. Yeah. All right, Everett, you had a question?
Yeah. So, just out of curiosity, what internal processes in a dying star causes a rapidly rotating magnetar? Is that just the remaining angular momentum, or?
You repeat your question, please? I'm sorry.
So, what internal processes causes a rapidly rotating magnetar? Is that just the remaining angular momentum, or is that something else?
Not too sure, but if I were to answer as best as I can, I would say yeah, it'll still be the remaining angular momentum from like the gravitational collapse. So yeah.